At the links on this page are demonstrations of electromagnetic induction, which is the generation of an electric field by a changing magnetic field. In these two videos, I was moving a magnet into and out of the center of a coil to generate a current in the coil. A viewer inquired as to what would happen if I moved the magnet laterally to or along the outside of the coil. This video demonstrates and explains what happens. Here is a bar magnet with a north and south pole. Running inside the magnet will be lines of magnetic flux density field, which will then emanate outside the magnet. Here is an illustration of those lines of magnetic flux density. So they'll emanate out the north pole and around the magnet and then back in the south pole. And you can see that the spacing between the magnetic flux density field lines will decrease as you move away from the magnet, indicating a reduction in strength of the magnetic flux density field. Here I have a galvanometer, and I have it connected to a 100-turn coil. So whenever there's a changing magnetic flux with respect to time inside the coil, there will be an electric field generated, and that electric field inside the coil will result in a current flow. So when I take this bar magnet and move it towards the coil, there's an increase in magnetic flux with respect to time, and I see a positive current generated. Now when I remove the magnet, there's a decrease in magnetic flux with respect to time, so I have a current flowing in the opposite direction. And the current that's generated is proportional to the rate of change of magnetic flux with respect to time. So I move the magnet slow, I get a small current. If I move it fast, I get a larger current flowing. I was asked the question, what would happen if instead of moving the magnet into and out of the coil, I was instead moving it around outside the coil? Well, as long as I'm moving the magnet, I am getting a change in magnetic flux with respect to time inside the coil. It's just that that change in magnetic flux with respect to time will be small because the magnetic flux density field falls off with distance from the magnet. But if you watch closely, when I'm moving it lateral to the coil, you can see a little bit of movement of the needle indicating I am generating some current. Similarly, if I'm moving it alongside the coil like this, again, I'm getting some change in magnetic flux with respect to time, and you can see a little bit of movement of that needle indicating a little bit of current being generated. Now the current generated is going to be proportional to the change in flux linkage with respect to time, which is the product of the change in magnetic flux inside the coil and the number of turns of the coil. So if I greatly increase the number of turns of the coil, then when I move the magnet outside the coil, I should be able to generate much more current. So here's a coil I wound that consists of 30,000 turns. So for the same changing magnetic flux inside the coil here, I'm going to get a much greater change in flux linkage. So let me now connect this 30,000 turn coil to the galvanometer. So now even when I move the magnet slowly, I generate current because of the large change in flux linkage with respect to time. So I have to be careful not to move it too fast and damage my galvanometer. Okay, so now let me move the magnet laterally. So you see there was a current generated because there was a changing magnetic flux inside the coil. So as I'm moving it towards the coil, there's an increase in magnetic flux, and I was generating a positive current. Now as I continue to move the magnet and away from the coil, now there's a decrease in magnetic flux inside the coil and a negative current generated. So now I'm going to take the magnet and move it alongside the coil. So as I'm moving it towards the coil, I noticed I was generating a positive current, and as it continues to move away, now it's a negative current. So as I'm moving it towards the coil, I'm generating an increase in magnetic flux and a positive current flow, and now as it's moving away, I have a decrease in magnetic flux and hence a current flowing in the opposite direction.